Have you ever heard of prions,
Oh, yeah.
right? Because for most of us, that word just triggers this immediate association with like some of the most terrifying, incurable brain diseases on the planet.
Yeah, absolutely. Mad cow disease, things like that.
Exactly. We think of this completely unstoppable biological cascade, right?
Mm.
Like a misfolded protein that just fundamentally breaks the normal functioning of a cell and then relentlessly self-replicates.
Mm.
It's basically the ultimate biological nightmare. But uh, what if the exact same biological mechanism that makes prions so unstoppable is actually the blueprint for the next technological epoch?
That cascade, the underlying geometry of how these proteins assemble, you are looking at one of the most efficient, resilient, and frankly versatile nanostructures permitted by the laws of physics.
Wow.
We're talking about repurposing the ultimate biological weapon into the ultimate architectural foundation.
And that is exactly what we are unpacking today. So for you listening, whether you're deep in material science or, quantum computing, or you're just tracking the very bleeding edge of civilizational infrastructure.
Which you should be.
Yeah, exactly, which you should be. This deep dive is designed to completely rewire how you think about the intersection of biology, physics, and computing. We're examining this massive visionary design manifesto published by an independent researcher, Zachary David Enfield.
Right back in March?
Yeah, March 2026. It spans multiple papers, addendums, just tons of research, collectively titled Prion and Amyloid Architectures, a total application framework.
And, the core mission of this deep dive is to synthesize Enfield's overarching thesis. Basically, that the fundamental structural motif of prions, which is called the cross-beta scaffold, can be engineered to build quite literally everything. Yeah. We're going to explore how this exact mechanism gives us, like, self-repairing submarine hulls, optogenetically printed biological tissue, DNA-based quantum logic gates operating at the thermodynamic floor.
Which sounds like sci-fi.
It does, but all the way out to stellar-scale Dyson swarms.
Okay, so to understand how we get to, stellar engineering,
Right.
we have to start way smaller, like at the 10 nanometer scale.
Right.
Because the foundation of this entire framework rests on that cross-beta architecture you mentioned. In a standard cellular environment, proteins fold into these complex globular shapes to perform very specific enzymatic tasks, right?
Yeah, usually.
But the cross-beta structure is totally different. It's an engineered nanocomposite.
Exactly. When we look at the cross-beta fibril under X-ray crystallography, we don't see a fragile globular machine at all. We see beta strands oriented perpendicular to the long axis of the fibril, and they're hydrogen bonded together into these intensely packed sheets. But the true engineering marvel here is how it handles mechanical stress.
Right, because it isn't just a rigid crystal.
No, not at all. The architecture features alternating layers of these highly rigid, hydrogen-bonded beta sheets separated by very specific protein side chains.
And what do those do?
Well, those side chains function as like extreme-scale shock absorbers. They dissipate kinetic energy before it can cleave the primary hydrogen bonds.
Which yields mechanical metrics that are honestly difficult to even contextualize. I mean, when you look at engineered polymeric amyloid fibers, they demonstrate a toughness of like 160 megajoules per cubic meter.
Yeah, which is insane.
It effortlessly surpasses spider dragline silk, and they achieve that toughness at 1/8 the density of steel.
Right.
But what really strikes me about Enfield's analysis is the chemical and radiologic resilience. We're talking about a biological material that survives boiling in concentrated sodium hydroxide.
Which would melt almost anything else.
Literally. It survives pure formic acid. It even withstands massive doses of gamma radiation.
Yeah, doses that would induce catastrophic lattice displacement in standard silicon logic chips or, copper wiring.
So how does it survive that?
The resilience comes down to the cooperativity of the hydrogen bond network. In a normal protein, if you denature one part of it, the whole thing tends to unravel.
Like pulling a thread on a sweater.
Exactly. But in a packed cross-beta sheet, the energetic barrier to break a single bond is massively elevated by the geometry of all the surrounding bonds. It's basically a structurally locked state.
Wow.
And this brings us to what Enfield identifies as the master engineering dial, which is the HBD, or hydrogen bond density.
Right, because if we are going to use this for total civilizational infrastructure,
Mhm.
we obviously can't just have one single rigid material. We need a tunable parameter.
Exactly. I mean, in our standard industrial paradigm, if you want to alter a material's mechanical profile, you have to fundamentally change its chemical composition.
Yeah, or it's macroscopic processing, like alloying, forging, tempering steel, stuff like that.
Right. But Enfield's framework utilizes amyloid logic. So the mechanical properties are directly proportional to the hydrogen bond density in the core of the fibril itself.
Okay, so if your application requires like structural steel-like rigidity,
You sequence the amino acids to hyperpack those residues. You maximize the HBD.
got it. And if you need a dynamic, easily fragmenting, rapidly replicating scaffold,
Then you intentionally introduce polar-rich or disordered cores to lower the HBD.
okay, let me make sure I'm getting this.
Mm-hmm.
It's almost like a baker tweaking a recipe, right?
Yeah.
Like you adjust the ingredients slightly to get either a super brittle cracker or a soft, chewy cookie.
Yes, exactly
If
that.
you're doing it at the 10 nanometer scale.
Right. The structural information isn't imposed from the top down. It's entirely encoded in the geometry.
Mm-hmm.
The amino acid sequence dictates the primary fold. The fold forces the surface geometry, and the geometry relentlessly drives the macro structure.
So the manufacturing process completely bypasses standard heavy industry. You don't need a multi-billion-dollar silicon fab
No.
or a blast furnace. You basically just take a protein-rich growth medium like, say, cyanobacteria in a bioreactor using sunlight and atmospheric carbon. You introduce a microscopic seed of the engineered amyloid, and it just self-replicates exponentially.
The marginal cost of material production essentially drops to zero.
Okay, let's unpack this,
Mm-hmm.
because we need to address the obvious biological risk here. If you are industrializing a self-replicating prion cascade in open-air bioreactors, you are basically playing with fire. If this breaks containment, how are we not dealing with a synthesized apocalyptic prion plague? It seems incredibly reckless.
Right, and it would be if they were using mammalian prion determinants. But Enfield is obsessively clear on the biochemical boundaries here.
Okay.
The architecture explicitly relies on yeast prion determinants. Specifically, they utilize the sub-35 protein combined with entirely synthetic de novo sequences.
Meaning they're made from scratch.
Yeah, exactly. And these specific biochemical pathways are demonstrably non-infectious to mammalian biology. They just lack the necessary conformational homology to interact with human PRP.
Oh, I see.
We're extracting the thermodynamic mechanism of self-assembly and entirely discarding the mammalian pathology.
So the replication is totally substrate specific. It can only cascade if it has access to a highly specific synthetic pool of monomers that literally don't exist in human biology.
Exactly. That completely isolates the threat.
Okay, so we have an indestructible, highly tunable, basically zero-cost structural material.
Mm-hmm.
But structural integrity is only the first requirement of a technological substrate, right? It needs to handle energy and information. And this is where Enfield pivots to the electronic properties of the fibril.
Yeah, this is a really critical transition in the manifesto. The structural applications are impressive, sure, but the electronic properties are what elevate it to a full civilizational framework.
Right.
We have to go back to some research from a couple decades ago. They demonstrated that the NM domain of the yeast sub-35 prion could be engineered to self-assemble into remarkably stable nanowires.
Oh.
Yeah. By introducing specific cysteine mutations into the sequence, they provided precise nucleation sites for gold nanoparticles.
Which means the fiber acts as a self-organizing template for metallization. So you don't have to carve a nanowire using, like, extreme ultraviolet lithography.
Right. No carving needed.
The protein literally just pulls the metal ions out of solution and patterns the wire autonomously.
Exactly. But the framework pushes far beyond just metallization. Relying on external metals still limits you. The real breakthrough comes from more recent studies which confirm that these amyloid fibrils possess intrinsic electronic conductivity.
They don't even need the gold.
Nope. The structural geometry of the cross-beta scaffold forces the aromatic rings of tyrosine residues into highly precise stacked alignments.
Oh, the pipey stacking.
Precisely. The electron clouds of those aromatic rings overlap so perfectly down the central axis of the fibril that they create a continuous quantum mechanical pathway.
That's
It
wild.
facilitates long-range hole-hopping transport over micrometer distances. And coupled with other recent findings, we see that these same tightly ordered water channels along the fibril axis facilitate proton conductivity that significantly exceeds most synthetic biomaterials.
So what does this all mean? If I'm understanding this, it's like a bucket brigade.
Okay, yep.
Instead of a solid copper wire, which is basically like a pipe of water, the tyrosine residues are like a line of people literally handing electrons down the chain.
That is a perfect way to visualize it. Yes, hole hopping.
So the exact same 10-nanometer fiber that serves as a load-bearing beam is simultaneously operating as an intrinsic charge carrier.
Yep.
But Enfield doesn't stop at conductivity, does he? He integrates the piezoelectric properties too.
Oh, yeah. When we look at divinylamine peptide nanocubes, which share the same amyloid structural logic studies, show a piezoelectric coefficient of 60 picometers per volt.
Just huge.
It puts a biological self-assembling protein in the exact same piezoelectric class as zinc oxide.
That multimodality just completely breaks standard engineering assumptions. You have a material that directly converts mechanical stress into electrical voltage and vice versa.
Hmm.
Let's extrapolate the mechanics of that because the applications Enfield proposes are just staggering. Consider aeronautics. In a hypersonic aircraft, aerodynamic friction creates immense mechanical stress and heat on the hull.
Yeah.
Traditionally, that friction is pure parasitic loss.
Right. It's an engineering nightmare.
But if the structural skin of the craft is composed of this highly cross-linked amyloid composite, the intense mechanical pressure waves traversing the hull don't just dissipate as destructive heat. The skin piezoelectrically harvests that mechanical stress to directly power the aircraft's internal avionics.
Exactly. The greater the atmospheric friction, the higher your onboard power generation.
It creates a closed-loop thermodynamic system.
It really does. And if you scale that down to the in vivo biomedical level, the piezoelectric properties allow for entirely wireless, battery-free intervention.
Wait, like inside the human body?
Yes. Enfield cites recent methodologies where piezoelectric amyloid fibers are injected directly into a solid tumor matrix.
Oh.
When the targeted area is hit with external ultrasound, the acoustic waves mechanically compress and expand the fibers. That induced stress generates a highly localized electric field, which basically catalyzes the production of reactive oxygen species directly within the tumor microenvironment.
Wow, so it induces apoptosis, it kills the cancer cells wirelessly,
Purely by converting sound into localized oxidative stress.
and it leaves healthy tissue completely untouched, eventually just biodegrading into basic amino acids.
Exactly.
Similarly, the framework outlines sound-activated SIRS sensors, surface-enhanced Raman scattering. By linking these piezoelectric fibrils with silver nanoparticles, ambient acoustic noise flexes the nanotube, generating the voltage required to boost the Raman signal.
Right.
You get a highly sensitive chemical tensor powered entirely by the random background noise of the room it sits in.
But we do run into a fundamental geometric problem here.
What's that?
Well, if you have a material that grows exponentially through nucleated seeding, it's going to expand isotropically, it's going to grow in all directions simultaneously, resulting in this chaotic, tangled hydrogel, or just a macroscopic clump.
Right.
If you want to build a sensor array, or a microprocessor, or a replacement organ, you need highly deterministic spatial control over the self-assembly.
So how do you force a self-assembling cascade to trace a highly specific three-dimensional circuit? That exact problem is what drives the third section of the framework, which is prion optogenetic lithography.
Yeah.
Enfield basically merges the thermodynamics of prion assembly with optogenetics and standard photolithographic techniques.
It's a really brilliant synthesis. Optogenetics relies on photoreceptor proteins like Cry2 or LOV2, which undergo massive conformational changes when they absorb specific wavelengths of light. The LOV2 domain, for instance, has a flavin mononucleotide chromophore. When it absorbs blue light, it forms a covalent adduct that violently unfolds an adjacent alpha helix. Enfield's framework proposes genetically fusing these light-responsive domains directly to the synthetic prion sequences.
So you create a steric block.
Hmm.
In the dark, the optogenetic domain physically covers or locks the prion nucleation site.
Yes.
So the protein remains completely dormant in solution. But the millisecond you hit it with a highly patterned laser, say a 450 nanometer blue laser, the octogenetic domain snaps open, exposes the cross-beta nucleation interface, and the fibril instantly begins self-assembling exactly along the path of the light beam.
Exactly. We are fundamentally shifting from a mold paradigm, where you are constrained by the physical geometry of your tooling, to a light paradigm.
Wow.
You use holographic spatial light modulators to project vastly complex 3D interference patterns into a bulk solution of these dormant proteins. The light defines the precise mathematical geometry, and the protein cascade materializes that geometry at the molecular level.
Here's where it gets really interesting. You're essentially doing 3D printing without any moving parts, nozzles, or physical extruders.
Right.
It's like you aren't printing ink onto a page. The ink is floating in a swimming pool, and you are just shining a flashlight into the water. And wherever the beam hits, a solid structure freezes into existence,
That is exactly what's happening, and the resolution is only limited by the diffraction limit of the light you're using.
which is incredibly fine.
Very. Enfield applies this directly to food and tissue engineering. Current lab-grown meat struggles because you can't easily extrude the highly complex microarchitecture of a real muscle, the precise alignment of fascicles, connective tissue, vascular
Right, it
networks.
usually just comes out like a paste.
Exactly. But with optogenetic lithography, you shine a holographic interference pattern into a bioreactor, and the proteins simultaneously snap into the precise microarchitecture of a steak,
Molecule by molecule.
molecule by molecule. And extending that to regenerative medicine, you bypass external bioreactors entirely. You inject a viral vector, like an adeno-associated virus, carrying the genetic payload for these optogenetic structural proteins into a traumatic wound site.
Okay.
The patient's local cells express the dormant monomer. A clinician then projects a patterned light field matching the geometry of the missing tissue directly into the wound.
That is wild.
You dynamically write a customized bioresorbable regenerative scaffold directly into the living tissue, dictating exactly how the regenerating cells should migrate and align.
And because you control the sequence, you precisely tune the HBD so that the scaffold degrades thermodynamically at the exact rate the native extracellular matrix replaces it. It's basically a temporary architectural ghost written by light. So we now have an indestructible, electrically and protonically conductive material that we can instantly pattern into vastly complex 3D geometries using light.
Right.
We have the ultimate wires and the ultimate structural substrate. But any advanced infrastructure requires immense localized power generation. And this is where Enfield introduces the coalescent transducer.
Yeah. If you look at standard beta-voltaic nuclear batteries, which use isotopes like nickel-63, the efficiency is abysmal, typically hovering around 2.86%.
That's terrible.
It is. And the bottleneck is self-absorption. You have a macroscopic chunk of radioactive material physically adjacent to a semiconductor transducer.
Okay.
When an atom decays deep inside the isotope matrix, the emitted high-energy electron collides with the surrounding radioactive atoms. It loses its kinetic energy to localized heating before it ever reaches the semiconductor junction.
So that the power is wasted just traversing the source material itself.
Exactly.
But Enfield builds upon a really cool breakthrough recently where researchers demonstrated a coalescent transducer architecture. They completely eliminated the physical gap by integrating the radioactive isotope directly into the molecular structure of the transducer itself. By synthesizing a polymer where the radioisotope is covalently bonded to the luminescent and photovoltaic elements, every single decay event is perfectly coupled to the transducer. The result was an 8,000-fold increase in efficiency.
Which is just astronomical. And Enfield maps that exact molecular integration onto the prion framework.
Right.
He proposes utilizing CRISPR to insert specific uranyl binding motifs into the sub-35 structural sequence.
What are those?
These motifs are essentially molecular tweezers engineered with femtomolar affinity, meaning their binding constant is astronomically high, specifically for uranyl ions floating in standard seawater.
Wait, so as the cyanobacteria in your bioreactor or just an open sunlit pond synthesize the monomer, those proteins passively sequester trace uranium out of the water.
Yes.
And as the light-directed cascade forces them to self-assemble, the geometry locks those uranium atoms perfectly down the central atomic axis of the conductive fibril. You have integrated the radioactive source inside the transducer at the angstrom scale.
Exactly. And because we've established the multimodal nature of the fibril, Enfield describes a trimodal harvesting geometry.
Okay, lay that out for me.
When a sequestered uranium atom spontaneously decays, the architecture captures the energy through 3 simultaneous pathways.
3.
Yes, 3. First, the beta-voltaic channel. The emitted beta particles kinetically coupled directly with the pi-p stacked tyrosine electron clouds, instantly generating a directional current.
Right.
Second, the piezoelectric channel. The atomic recoil from the decay violently vibrates the fibril lattice, generating a pronounced piezoelectric voltage spike.
Wow.
And third, the thermoelectric channel. Any residual thermalization creates a massive thermal gradient across the 10-nanometer diameter of the fiber, which is harvested via the Seebeck effect.
It's absolute merciless thermodynamic efficiency.
Yeah.
You're extracting three distinct forms of electrical power from a single atomic decay event
Yeah.
housed in a self-assembling biological fiber that basically costs nothing to manufacture. Yep. But wait, I want to make a critical distinction here, because when people hear engineered biology and uranium, they immediately conceptualize a biological nuclear reactor. Are we talking about building biologically active nuclear reactors? Because that sounds like a meltdown waiting to happen.
Yeah, and that is a fundamental and dangerous mischaracterization of the physics involved. A nuclear reactor relies on controlled, sustained fission.
Right.
You are actively utilizing neutron bombardment to split atomic nuclei in an exponential chain reaction. The coalescent transducer architecture does absolutely none of that.
Okay.
This is a solid-state, entirely passive energy converter. It operates purely on the spontaneous, natural baseline decay of the isotope. There is no chain reaction, no criticality, and therefore no physical possibility of a meltdown.
Exactly. It's the difference between building a massive combustible bonfire to drive a steam turbine versus setting up a highly sensitive microscopic windmill to catch a gentle, naturally occurring breeze. It just so happens this breeze is baseline isotopic decay.
Exactly. Conflating the two just ruins the science.
So with power generation solved at the nanoscale, we hit the computation layer. You can't run a civilizational infrastructure without processing data. Enfield's 8-layer architecture introduces a computational framework operating at the thermodynamic floor of physics.
Right. And to understand the efficiency gains here, we have to look at how it fundamentally abandons the von Neumann silicon architecture. In Enfield's model, the primary storage medium is DNA. DNA stores data in quaternary states, A, C, T, G, which doubles the information density per operation compared to binary logic. The highly conductive prion fibers we've been discussing act as the physical logic interconnects, utilizing rapid conformational shifts at their junctions as logic gates.
But every CPU needs a clock pulse to synchronize operations.
Right.
Like silicon processors use a crystal oscillator. In this biological architecture, the clock is terahertz radiation. The hydrogen bonds holding the DNA base pairs together possess specific resonant vibrational modes in the terahertz frequency range. By pulsing the system with highly calibrated terahertz radiation, you can resonantly unzip and rezip the DNA strands in trillionths of a second, yielding read and write speeds that rival cutting-edge silicon.
And this introduces the most common, seemingly fatal objection to the architecture. Critics look at terahertz radiation and immediately point out that water is a massive absorber of terahertz frequencies.
Right, and DNA and amyloid proteins operate exclusively in an aqueous environment.
Exactly. Therefore, the argument goes, pulsing the system with terahertz radiation will result in catastrophic dielectric heating. The water will boil, denaturing the proteins and instantly destroying the computer.
That seems like a hard limit in physics. But Enfield demolishes the objection by pointing to a recent paradigm shift called thermodynamic computing.
Yeah.
The assumption that heat destroys computation is only true if you are fighting the thermal environment. Thermodynamic computing harvests it. Researchers demonstrated that you can utilize highly specific thermal cycles to restore enzyme-free DNA logic circuits from their equilibrium states back to out-of-equilibrium chemically reactive states.
The dielectric heating from the T8's absorption isn't a bug, it is the resetting mechanism. It provides the exact thermodynamic work required to power the subsequent logic operation.
That's brilliant.
But Enfield goes even deeper, directly addressing Landauer's principle.
Right.
Rolf Landauer famously proved that any logically irreversible manipulation of information, such as erasing a bit or merging two logic paths, must be accompanied by a corresponding increase in the entropy of the environment.
You basically have to pay a thermodynamic tax for erasure.
Yes, which manifests as heat.
Right, which is exactly why modern data centers require massive industrial cooling infrastructure. They're constantly overwriting and erasing billions of bits per second.
Exactly.
So if the thermal floor is a hard barrier to standard computation, how does the amyloid architecture bypass the Landauer limit?
By relying exclusively on logically reversible computation and holographic geometric propagation.
Explain that.
Well, when a conformational state change propagates down the prion fibril, it doesn't overwrite or erase the previous state. It geometrically couples with it.
Oh, I see. Because the architecture preserves the history of the logic state, meaning it can theoretically be run backward to its initial condition. It performs zero erasure.
And without erasure,
It completely sidesteps the Landauer thermodynamic tax.
it computes at the absolute thermodynamic floor.
Yes.
It's like early engineers complaining that wind resistance was slowing down their cars, and then someone invents a turbine that uses that exact headwind to power the engine. The noise became the fuel.
That's a great way to put it. And Enfield extrapolates this to what he calls Brownian prion computing for ultra-low power needs.
Okay.
Imagine a microscopic sensor array injected into the human bloodstream or seeded into the atmosphere of a gas giant. It doesn't even utilize the T-Hertz clock.
Then what does it use?
It simply harnesses ambient Brownian motion.
Oh, the random chaotic thermal vibrations of the water molecule.
Exactly. It uses those to gently drive the reversible logic gates forward. The ambient temperature of the environment literally powers the computation for free.
Wow. So we have DNA serving as the quaternary deep storage archive. We have prion fibrils acting as the structural motherboard and logic interconnects. We have T-Hertz radiation acting as the system clock, and heat acting as the reset mechanism.
Right.
But a static system cannot dynamically respond to its environment. It requires an execution layer. Which brings us to section 6, the integration of RNA.
Yeah.
If DNA is the hard drive and the prion fibril is the motherboard, RNA functions as the real-time execution layer, effectively the RAM. RNA aptamers and riboswitches act as analog-to-digital converters within the biological computer.
And the mechanics of a riboswitch are perfect for this. An aptamer domain physically binds to a specific target molecule in the environment, say a topsin or a specific metallic ion.
Right.
When it binds, it triggers a massive secondary structural change in the expression platform, often forming a pseudoknot. In Enfield's architecture, this mechanical conformational shift applies direct allosteric tension to the integrated prion fibril.
So the RNA physically pulls on the logic gate.
Exactly. It instantly alters the flow of electrons or the conformational state of the network. It allows the computational matrix to actively rewrite its own logic pathways in real time based on environmental stimuli.
But the architecture doesn't stop at classical quaternary logic. Enfield integrates room temperature photonic quantum computing.
Yeah, this is where it gets really crazy.
The amyloid scaffold is uniquely adapted for the KLM architecture, Mill-Laflamme-Milburn, which is the foundational blueprint for linear optical quantum computing.
And the KLM architecture requires three things: single photon sources, linear optical elements like beam splitters and phase shifters, and photon detectors. It generates quantum entanglement through post-selection on those detectors.
Right.
The amyloid architecture provides all of this intrinsically.
Because the key is chirality, right?
Yeah.
The cross-beta structure naturally possesses a helical twist.
Yeah.
If you utilize the metallized variations we discussed earlier, that chiral fiber acts as a highly selective optical waveguide. It inherently separates left circularly polarized light from right circularly polarized light through circular dichroism.
And then you attach quantum dots to specific nodal points on the fibril to act as your single photon sources. The physical junctions where fibrils intersect act as your phase shifters and beam splitters, and the piezoelectric components serve as your photon detectors.
You literally have a self-assembling room temperature quantum computer.
Yeah.
And the precedent for this already exists in nature. Enfield draws heavily on the phenomenon of vibronic coherence observed in photosynthesis.
Right, like in green sulfur bacteria. They manage to transfer excitation energy with near-perfect efficiency by maintaining a quantum coherent state at room temperature.
Which is usually impossible because of environmental noise.
Right.
Right.
Exactly. But the protein matrix perfectly tunes the environmental noise to prevent decoherence. The tightly packed hydrogen-bonded geometry of the cross-beta scaffold mimics this exact vibronic environment, allowing for robust quantum electron tunneling along the tyrosine pathways without cryogenic cooling.
Nature has been running room temperature quantum operations for billions of years. Enfield's framework simply provides the compiler to program it. So let me ask you this. If DNA is the hard drive and RNA is the RAM, what does that make the prion fiber?
The prion fiber is the motherboard and the physical circuitry. It's the structural highway that propagates the signal across space.
Okay, so let's take stock of the total stack. We have integrated electron and proton transport, piezoelectric harvesting, optogenetic spatial patterning, coalescent nuclear transducers, RNA execution, thermodynamic quaternary logic, and photonic quantum computing.
It's a lot.
It's everything. Every single one of these massive infrastructural layers is fully encoded within the DNA of a single microscopic organism. The entire industrial base of a civilization is compressed into a nanogram of genetic data.
Yeah.
Which leads us to the final and frankly most staggering implication of the framework. the holographic node and the redefinition of Type III civilizations.
Right. We measure civilizational advancement using the Kardashev scale. A Type I civilization controls the energy of its planet, Type II its star, and Type III its galaxy.
Mm-hmm.
But Enfield points out a critical, blinding assumption built into Kardashev's premise, the assumption of dualism, the assumption that the civilization is separate from its infrastructure.
Like, we assume a civilization must build massive factories, mine vast quantities of raw materials, launch heavy mechanical fleets.
Exactly, to construct something like a Dyson swarm. But under the Prion architecture, that dualism vanishes. The biological node is the infrastructure.
Wow.
You don't launch a fleet of mining ships to a distant star system. You launch a seed package. You send a microscopic capsule containing a few nanograms of engineered cyanobacteria and viral nanites.
And it hits a carbon-rich asteroid in a foreign solar system. The cyanobacteria immediately begin processing atmospheric carbon and localized minerals powered by starlight.
Yeah.
The optogenetic protocols trigger. It begins self-assembling an array of coalescent transducers and piezoelectric waveguides.
It begins building a Dyson swarm, molecule by molecule, entirely autonomously. And this maps perfectly onto holographic information theory, specifically utilizing the Bekenstein-Hawking entropy formula.
Okay, remind me how that works.
In theoretical physics, a black hole stores all the information regarding its three-dimensional volume purely on its two-dimensional surface area, the event horizon. The boundary contains the totality of the volume.
The part contains the whole.
Exactly. The geometry of the growing prion fibril operates on the exact same informational mathematics. The complete structural and computational future of the macroscopic network is completely determined by and encoded upon the two-dimensional surface of the growing fibrillar tip.
Mind-blowing.
Because every single biological unit contains the total capacity to generate the entire infrastructural stack, the node logically precedes the scale. You don't need to slowly expand a galactic empire over millions of years to achieve Type III status.
A civilization is functionally a Type III civilization the exact moment the biology works, because the total capacity for galactic saturation is inherent in the code of the very first microbe.
Exactly.
And the structures this biology builds are actively manipulating astrophysics. The Dyson swarm the biology constructs isn't just passively catching photons. Because the swarm is composed of highly conductive chiral fibrils, it acts as an inconceivably massive electromagnetic phase array.
Right.
Enfield details how this swarm can utilize magnetic acoustic compression to literally squeeze the star it orbits. It generates an oscillating poloidal and toroidal magnetic field that couples directly with the stellar plasma, inducing massive acoustic waves that compress the stellar core.
It functionally turns a main sequence star into a managed stellar tokamak.
It artificially elevates the fusion rates or throttles them back based on the network's energy demands.
And it scales to communication, too.
Yeah.
Utilizing the Gertsenstein mechanism, the swarm can facilitate galactic scale communication. Well, the mechanism describes the conversion of electromagnetic waves into gravitational waves when in the presence of a massive static magnetic field. The energy-momentum tensor of the high-frequency electromagnetic wave couples directly to the metric tensor of spacetime.
Okay.
By utilizing the massive rotating magnetic field of the stellar tokamak, the swarm can modulate electromagnetic signals into localized gravitational waves.
Which gives you a communication network entirely immune to signal degradation.
Mm.
Gravitational waves don't interact with interstellar dust, gas, or plasma. You achieve pristine, real-time data transmission across the entire galaxy.
Yeah.
But wait, we have to address the terrifying reality of what we are discussing. Launching microscopic, self-replicating biological seeds that systematically dismantle asteroids to build star-crushing megastructures. Doesn't launching self-replicating biological seeds across the galaxy sound like the ultimate invasive species? How do we stop it from turning the universe into paper clips, or in this case, amyloid fibers?
It's a very fair question, and Enfield dedicates a massive portion of the framework to what he calls the ethical architecture. This cannot just be an exercise in unchecked exponential growth. The engineering protocols require a rigid, mathematically proven two-level kill switch.
Okay, what's level one?
First, the biology is engineered to be strictly geographically self-limiting. The replication cascades are hard-coded to only initiate in the presence of specific, rare isotopic substrates found on targeted asteroids, and they utilize quorum sensing to immediately halt replication once specific volumetric boundary conditions are met.
So it physically cannot replicate in a standard planetary atmosphere. The chemical triggers simply aren't there.
Correct. And second, the entire computational matrix remains fundamentally susceptible to highly encrypted RNA interference Q codes broadcast from the home system via that gravitational wave network.
Oh, wow.
If the local network registers a severe mutation or attempts to expand beyond its programmed boundary, the kill signal triggers an allosteric cascade that structurally dissolves the critical hydrogen bonds in the central prion nodes.
It immediately reverts the entire megastructure back into inert amino acids.
Exactly. The ethics of containment and dissolution are engineered to be structurally superior to the mechanisms of expansion.
It is an absolutely staggering synthesis. We started this discussion by examining the microscopic cross-beta architecture of a misfolded protein, the exact mechanism that drives incredibly destructive brain diseases.
Yeah.
And by extracting that thermodynamic logic and discarding the pathology, we arrive at a blueprint for a Landauer-efficient, self-replicating, stellar-scale civilization grown entirely from sunlight, carbon, and geometry.
It forces us to completely reevaluate our definitions of machinery, biology, and infrastructure. When the geometry itself is the computer, the factory, and the power grid, the limits of standard engineering disappear.
And while constructing a managed stellar tokamak might be centuries or millennia away, the foundational components we discussed today, the optogenetic tissue printing, the piezoelectric amyloid sensors, the thermodynamic quaternary DNA logic, gates, these aren't theoretical musings. These mechanisms are actively being demonstrated and refined in laboratories right now in 2025 and 2026. Zachary David Enfield's manifesto is a rigorously researched roadmap of current capabilities. The future of civilizational infrastructure is literally already sitting in a bioreactor.
Which leaves us with a necessary, provocative thought directly from Enfield's conclusion. He states, the question is not whether prion and amyloid architecture will fundamentally transform the physical infrastructure of civilization. The thermodynamics dictate that it must. The question is whether the civilization that initiates the cascade will possess the cognitive architecture to understand what it is holding.
It changes everything about how you perceive the physical world. The next time you look at a biological system, don't just see a messy, fragile organism. See the ultimate self-writing geometry of the universe. Because sometimes, the exact mechanisms we fear the most are hiding the blueprints we need to survive the future. Thank you for joining us on this deep dive. Keep questioning the consensus, keep looking at the underlying structures, and we'll see you next time.